So welcome to this session. Now we go to the Cayley-Hamilton theorem. The statement of the Cayley-Hamilton theorem is every square matrix satisfies its own characteristic equations. So we know that one. So square matrix having the characteristic equation. So that matrix, we can replace that matrix in the characteristic equation, it will be satisfied. So that's the theorem says every square matrix satisfies its own characteristic equations. So where we could apply the Cayley-Hamilton theorem in number 1, the inverse of any non-singular square matrix can be calculated. The higher positive integral power of the matrix A can be found out. So example number 1. So verify Cayley-Hamilton theorem for the matrix. So the square matrix is given. So 3 by 3 matrix. So we want to check the matrix satisfies the Cayley-Hamilton theorem. So first we go to find the characteristic equations. So we need to find the characteristic equation. So already we know that one characteristic equation is determinant of A minus lambda I is equal to 0. Therefore here we can let the given A is 3 by 3 matrix. So the general form of characteristic equation is lambda cube minus s1 into lambda square plus s2 into lambda minus s3 is equal to 0. So therefore we need to find s1, s2, s3. So s1 is nothing but sum of the main diagonal entries. So you can sum the main diagonal entries, you will get s1. So s1 is nothing but 4. So then s2 is sum of the minus of the main diagonal entries. Therefore we go to find the sum of minus of the main diagonal entries. So we calculate it, we will get s2 is equal to minus 20. Then s3 is determinant of matrix A. So find the find the determinant of the matrix A, will get 35. Therefore s3 is equal to 35. Replace s1, s2, s3 in the general form. We will get the characteristic equation is lambda cube minus 4 lambda square minus 20 lambda minus 35 is equal to 0. So by Cayley-Hamilton theorem, so replace lambda is equal to A, we will get the characteristic equation. So we got the characteristic equation, instead of lambda we go to replace A, therefore we will get A cube minus 4A square minus 20A minus 35, I is equal to 0. Therefore this we want to prove actually. So every square matrix, here A is a square matrix, every square matrix satisfies its own characteristic equation. So this is the characteristic equation. So if you replace that one, means the final solution will be 0 matrix. Therefore here I is the identity matrix. In our hand we have A is the matrix, that is given matrix. Therefore we need to find A square and A cube. These two things we need to find. After found A square and A cube, we can replace it here. Surely if it is verified means we will get a 0 matrix. So therefore we need to find A square. So A square is nothing but A matrix into A matrix. Therefore we can calculate by, we can multiply by the 2 matrix. So we will get these entries. Similarly we need to find A cube. A cube is nothing but A into A square. So therefore we will get this case. So we got A square and A cube. So replace it in our Hamilton in the equations. So replace A cube minus 4, we can replace the A square minus 20 into A minus 35 into I. So we can simplify this, multiple the 4 inside, the multiple the 4 with all the entries, we will get this matrix. Next we go to multiple this 20 with all the entries. So we will get this case. Next multiple minus 35 with all the entries. So we will get this. Now we can sum of this matrix. Therefore 135 plus 80 plus 20 minus 35 will get the entries. All the entries tend to 0. Therefore the Cayley-Hamilton theorem is verified. The statement of the Cayley-Hamilton theorem is every square matrix satisfies its own characteristic equation. So hence Cayley-Hamilton theorem is verified. So we go to see one more problem. Find the characteristic equation of the matrix A is given. So hence find A inverse and A power 4. So therefore A is equal to given matrix, the characteristic equation is, so this is the characteristic equation, we need to find S1, S2, S3. So therefore the characteristic equation is this. So next by Hamilton theorem, so replace lambda is equal to A, we will get this. So next we need to find A inverse, therefore I can multiple both sides by A inverse, so we will get this. So A inverse into A cube is A square, similarly A inverse into A square is A into A inverse is identity matrix, and identity matrix into A inverse is A inverse. So therefore we need only A inverse, bring the remaining terms in your right hand side, so multiple the equation 1 by A, so we will get, so A power 4. So A inverse we got now, next we want to find A power 4. So the A power 4 is equal to this, so replace all those things, we will get this. Therefore we need so we need to find only A square. Okay, so A square means A into A is A square, so therefore so replace your A square in both the equations, equation number 2 and equation number 3. If you replace the A square, A and I, we will get the A inverse. Similarly replace your A square, A and I, we will get A power 4. So A square, so replace it, so we will get A inverse is equal to 1 by 4 into the matrix. Similarly we can replace A square, A and I, we will get A power 4 is equal to, so this entries, this is A power 4. Next, using the Cayley-Hamilton theorem, find A inverse. Suppose if it is verified means we want to prove it. So here they said that you can use only Cayley-Hamilton, we can utilize it, no need to verify. So therefore given A matrix, the characteristic equation is this. So the general form of characteristic equation is lambda cube minus S1 into lambda square plus S2 into lambda minus S3 equal to 0. The S1 is nothing but sum of the main diagonal entries, we will get S1. So S2 is the sum of the minus of the main diagonal, so S2 is equal to minus 1. Similarly determinant of A is S3 is equal to 9. The characteristic equation is lambda cube minus 3 lambda square minus lambda minus 9. Therefore from this we can replace lambda is equal to A, we will get this. Therefore we need to find A inverse. I can multiple A inverse on both the sides, so we will get this. From this keep A inverse only one side, the remaining we bring it to another side, we will get this. So now we need to find A square. So replace A square in equation number 5. So we will get 9 A inverse equal to this, replace A square, A and I. So therefore A inverse is equal to 1 by 9 into these entries. Next we need to find similar method, find A inverse if A is equal to using Cayley-Hamilton theorem. So A is given, the characteristic equation is this. So therefore the general form of the characteristic equation is lambda cube minus S1 into lambda square plus S2 into lambda minus S3 is equal to 0. So therefore from this we need to find S1, S2, S3. S1 is nothing but sum of the main diagonal entries, so S1 is equal to 2. S2 is the sum of the minus of the main diagonal entries, so S2 is equal to minus 5, and S3 is equal to determinant of the matrix, S3 is equal to 6. So replace the S1, S2, S3. By Cayley-Hamilton theorem, we can replace lambda in terms of A, so multiplied A inverse on both the sides. From this we will get A inverse, we need to find A square, so A into A, so multiply it, we will get a square value. So replace your A square, so we will get A inverse is equal to 1 by 6 into this, therefore this